Hi, in this session we'll continue converting decimal number to other number systems and back from other number system or other base numbers to decimal numbers. So I hope with all three different methods been discussed, it's clear how to convert decimal number into binary number system. Now we'll talk about how to convert decimal numbers to different number systems. It could be any. So we'll take a couple of examples to understand the basic methodology. That binary we have already discussed. It has, see, binary says 0 and 1. That means the binary number any number represented by binary number system has just two digits. The number is represented with the combination of 0 and 1s, whereas there is another number system that's called octal, which is represented using 8 digits starting from 0 to 7 to represent any number. So in total there are 8 bits, hence the base of this octal is 8. Now if we have to convert a decimal number, that is 34 in this scenario, to an octal number, then we need to divide this 34 by 8. So if you divide 34 by 8, we get 4 as quotient and 2 as remainder, right? So this quotient is again divided by 8 to get 0 as quotient and 4 as remainder, right? So hence the 34 in decimal is equivalent to 42 in octal, right? There is another number system called hexadecimal number system, in which we have 15 different digits to represent the number, any number rather. Anyways, so how to represent those 15? So 0 to 9 representation goes as it is, and 10 is represented using A, 11 is represented using B alphabet. Similarly, the 15 number is represented using F alphabet. Now let's convert the decimal number into hexadecimal. As the number of total digits used to represent a hexadecimal number is 16, therefore we divide 34 by 16, we get 2 as quotient and 2 as remainder. Again dividing this 2 by 16, we get 0 as quotient and 2 as remainder. So therefore 34 in decimal is represented as 42 in octal and 22 in hexadecimal, right? So let's generalize this process of converting into any base number system. So in general, for example, we want to convert our decimal number into a number system that has a base 5. So we need to divide it by 5, and as the total number of digits used to represent any number in 5 based number system is 5 starting from 0 to 4. So we divide 34 by 5 to get 6 as quotient and 4 as remainder. We dividing this 6 by 5, we get 1 as quotient and 1 as remainder. Now dividing this 1 by 5, we get 0 as quotient and 1 as remainder. Hence, if you want to represent a decimal number 34 in terms of 5 based number system, the answer is 114 to the base 5, right? So this helps us to generalize the concept and make us understanding clear that we can convert decimal number to any base number system by dividing and recording the remainders in a reverse order. Okay. In hexadecimal representation, as we have discussed in the previous slide, 0 is represented by 0, 1 is represented by 1, so on till 9. So till 9, every digit is represented by itself, but from 10 onwards, for example, 10 is represented as A alphabet, 11 is represented as B alphabet, and so on till 15th, which is represented as F alphabet. Now let's see how it works. Suppose we have a number 334 in decimal. We want to convert it into hexadecimal. We divide it by 16 as we have seen in the previous slide, and we get 14 as remainder and 20 as quotient. Now we divide this 20 by 16 to get 1 as quotient and 4 as remainder. Now Dividing this 1 which is quotient by 16, we get 0 as quotient and 1 as remainder. And as per our terminal protocol, we go in the reverse order. So 334 in decimal is equivalent to 14e. Now E means 14. So we need to represent this 14 with one digit. So we are using or the protocol uses or suggests us to use E at the place of 14. So we write 1 in the reverse order, then 4, then instead of writing 14 we write E. So 334 in decimal is equivalent to 14e in hexadecimal. I hope it's clear. Anyways, coming back to the number system formula, or rather the equation that we discussed in the last session, where n is equal to nth digit into base to the power n, so on till 0th digit or the first digit from the right into base to the power 0. Now any number we want to convert into back to decimal from any of the number system, that could be octal, hexadecimal, or to the base 5 or to the binary, we can use this equation to convert it back to n, capital N, which will be a decimal number. Let's see how we can do this. For example, we take the decimal number system which is 524. If you do remember, we discussed this particular example in the keeping each digit in one box. Every box should have only one digit and has only one label. Label starts, because this decimal number base is 10, so we start from the right hand side and give the power as 0, starting from 0, 0, 1, 2. We go till 2 because we have total 3 digits, right? Starting from the right to the left, the power of the base 10 in this case, keep increasing for the label starting from 0. Now when we equate this to calculate the decimal number, say 5 into 10 to the power 2, 10 to the power 2 plus 2 into 10 to the power 1 plus 4 into 10 to the power 0. Okay, so this becomes 5 into 100 plus 2 into 10 plus 4 into 1, that is 524. This is equivalent to 524 because 524 was in itself a decimal number. Now let's use this equation to convert numbers in binary, octal and hexadecimal, or maybe in any other base number system back to decimal. So let's start with converting a number from binary to decimal. So let's have a number, say 1000010 in binary, and we want to convert this into decimal. So we need to place these digits one in each box first, right? So every box should have only one digit and has only one label. Starting from the right to the left, the power of the base, which is 2 in this case because we are converting a binary number, keep increasing for the labels starting from 0. So we place 1, 0, 0, 0, 1, 0, 1 digit in each box. Now let's start giving powers to 2 starting from the right hand side. 2 to the power 0, then 2 to the power 1. It will go till we have the number digits in boxes. So it will go from 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5. Now converting this or calculating the decimal value out of this binary number, what we do is we write 1 into 2 to the power 5 plus 0 into 2 to the power 4 plus 0 into 2 to the power 3 plus 0 into 2 to the power 2 plus 1 into 2 to the power 1 plus 0 into 2 to the power 0, right? So it becomes 1 into 2 to the power 5, that is 32, plus 0 into 16 plus 0 into 8 plus 0 into 4 plus 1 into 2 plus 0 into 1, that is equal to 32 plus 2, that is 34. which is in decimal. I hope it's clear to everyone. Great. Let's move ahead. So now we are trying to convert the octal number into decimal number. So for example, we take 142 as octal number. The protocol to convert is same. Again we place each digit of this octal number 1 in each box, and then we start from right to left. We give the power of the base, that is 8 because this is octal, keep increasing for the labels starting from 0. So 8 to the power 0, then 8 to the power 1, 8 to the power 2. So the equation is like this to convert it into decimal. 1 into 8 to the power 2 plus 4 into 8 to the power 1 plus 2 into 8 to the power 0. So it becomes 1 into 64 plus 4 into 8 plus 2 into 1, that is equal to 98 in decimal. Hence 142 in octal is equivalent to 98 in decimal. Last but not the least is hexadecimal to decimal conversion. Suppose the same number 142 is in hexadecimal. The protocol is again the same. We place this each bit of this, or rather each digit of this number 1 in each box, and then starting from the right to left, the power of the base, which is 16 in this case, keep increasing for the labels starting from 0. So we have 16 to the power 0, 16 to the power 1 and 16 to the power 2. Hence the equation becomes like this: 1 into 16 to the power 2 plus 4 into 16 to the power 1 plus 2 into 16 to the power 0, that is equal to 1 into 256 plus 4 into 16 plus 2 into 1, that is 256 plus 64 plus 2, that is 322. Hence 142 in hexadecimal is equivalent to 322 in decimal, right? There is an important observation which you might have noticed, and I would really like to highlight that right now, is as the base value decreases, if you can see in the diagram, hexadecimal has 16, decimal has 10, octal has 8 and binary has 2. As the base value decreases, the value of the number would be greater than or equal to value of higher base value. So decimal value of 10 would always be greater than or equal to 10. So it's a generalized observation, right? For example, if we talk about representing 1, so 1 will be represented in all 4 formats the same way. We will only have one digit to represent 1. That's why we say it's either equal or greater than, right? Usually it's usually greater than the, right? This was just an observation. The computer at the hardware level understands only binary numbers, but we need to understand 4 intermediate number systems used for better human interaction. Those are decimal, binary, octal and hexadecimal. In the next session, we will try and understand the binary number system. Thank you.